This next video has to do with what's called the orbital hybridization. And so this is all about covalent bonding, and it is really just theory, but it makes a whole lot of sense when one considers what we actually know about bonding, and so it's taken as probably mostly correct. Okay, so uh, recall that covalent bonds, they are considered to be overlapping electrons, and what we mean by, or electrons that are being shared, and what we mean by that is that we have an orbital overlap. So recall that electrons, they're in particular orbitals, particular shapes. In order to share electrons, you have to have overlap of the orbitals for those outermost electrons. And so for hydrogen, consider hydrogen. When we get molecular hydrogen, we have an individual hydrogen atom moving close to an individual hydrogen atom. At some point, they'll get close enough where the electron orbital or the orbital for that electron, the orbital for that electron will overlap, and all of a sudden you'll have this bond that forms. Now it's shown back down here with a little bit better drawing. But again, you have two hydrogen atoms coming close. Those little spheres are showing the 1s electron that exists in a hydrogen, and a bond occurs when the part of that orbital essentially overlaps with part of the orbital of the other. And so this is what is called valence bond theory. So bonds form from direct overlap of half-filled valence orbitals. So it's important that it's half-filled. If it's fully filled orbital, that means there's no place left for the electrons to go, right? And so things have to be half-filled in order for electrons to actually have a space to fill. And so not only do you have overlap of sigma, s orbitals, but you can also have overlap of an s orbital with a p orbital to form a bond, or two p orbitals that can form bonds. And so all of these different types of bonding occur when we get covalent bonding. We essentially have an empty or half-filled orbital that overlaps with another half-filled orbital, and all of a sudden that orbital becomes fully filled. Now there's a reason why these particular orbitals have a very, very defined distance, or excuse me, these particular nuclei have a very, very defined distance, and that has to do with the reaching the minimum energy possible when a bond occurs. So consider the energy of a particular bond or of overlap of these orbitals as a function of the distance of the two nuclei. So if the nuclei are at this just perfect distance, you get a minimization of the energy for that orbital overlap. If, however, you start moving the nuclei closer and closer together, moving this way on your x-axis, the energy starts shooting up and goes up at an exponential rate. The reason for this is because the nuclei are starting to get close together and they start repelling each other, and that increases the energy for the system. However, as you move the atoms further and further apart, their potential energy also the energy also increases, because now you're not getting the electron nuclei, so the electron nuclei attraction, and so there's this kind of essentially a sweet spot where you get the attraction from one of the electrons of one of the atoms being attracted to the nuclei of the other atom, and that balancing with the nuclei repulsion and the electron repulsion. You get further and further away, you don't get that attraction, and that actually increases the energy of the two atoms overall. And so bonding occurs. When bonding occurs, it actually is, in general, it's a net benefit. It lowers the energy for the overall system.